Assignment 2.3, Fatigue and Recovery. So fatigue, what is it? It's the exhaustion of muscle, extreme tiredness, or pain or aching of a muscle. So there are a few different types of fatigue. So we've got chronic, which is when an individual has a weak immune system from overtraining or inadequate recovery, or both. General fatigue is just when someone is physically, psychologically, or even mentally weak. And local fatigue, which is when fatigue is localized in muscle after a repeated use with a lack of recovery. So there's several different determinants of fatigue. We've got the type of activity, whether it be continuous like a marathon or intermittent like a football game. We've got the energy system that's being used, so ATP/PC system, lactic acid system, or the aerobic system. Which muscle fibres are being used, so fast glycolytic, slow oxidative, or fast oxidative glycolytic fibres. We've got the duration and the intensity of the exercise, the fitness level of the athlete, and the type of muscle contraction, whether it be isometric, concentric, or eccentric, which is the more fatiguing contraction. So a few different causes of fatigue. We've got depletion of energy sources, like glycogen, neuromuscular function, so someone might just not be physically fit enough to perform and therefore they'll fatigue. Thermoregulation, so someone might not be able to cool themselves down efficiently and therefore will fatigue. Accumulation of waste products like lactate when using the lactic acid system, or carbon dioxide when using the aerobic system. Also ATP resynthesis, so if that isn't occurring, then there's going to be no ATP for muscle contractions. Other things that cause fatigue include emotions, motivation, experience of an athlete, altitude, pain, core temperature, and stimulants like caffeine. So maximal exercise, for example a javelin throw or 100-metre sprint, are very, very low in duration but very high in intensity. For example, the javelin throw just uses one molecule of ATP, it's a simple 3-second movement, whereas the sprint does use more than that. It uses the PC system, it uses phosphocreatine as its main energy source. So fatigue can be prevented during these two activities by taking phosphocreatine supplements. So the more phosphocreatine that the athlete has, the more ATP that can be resynthesized quicker. This is more applying to the sprint. Now, if we're looking at the javelin throw, it's so short in duration that fatigue won't have a huge effect on the performance at the time. However, if we're looking at the sprint, the legs of the athlete will ache, and potentially the arms of the javelin thrower, after the sprint has finished. However, you could argue that less power can be generated by the sprinter actually during the race. So these types of maximal exercises take a long time to recover from. So as we can see in the graph, there is a very large oxygen deficit, which is just a temporary shortage of oxygen during the exercise. Now, this is because it's an anaerobic activity, so the oxygen isn't being used during the actual exercise. Because of this, there is a much larger EPOC, which is the excess post-exercise oxygen consumption. So therefore, more oxygen is consumed in recovery because of the larger oxygen deficit. So oxygen is required in order to repay the oxygen debt. So the type of recovery that happens after this exercise is a lactic fast recovery. So the oxygen consumed during EPOC is used for resaturating myoglobin and hemoglobin with oxygen, which just takes a few minutes. Also, resynthesis of adenosine triphosphate, or ATP, and phosphocreatine stores using the energy produced by this aerobic system during recovery. So moving on to moderate exercise, it's moderate in duration and moderate intensity, as it says there, like a 400-metre sprint. So the energy system uses the lactic acid system, and the main energy source is glycogen. Because of the lactic acid system being used as the system, lactic acid and both hydrogen are produced as a waste product, increasing the acidity. So hydrogen ions are what make the lactic acid an actual acid. They interfere with nerve impulses travelling to and from the muscles, and therefore slow energy reactions down. This is because the acidity denatures the enzymes, therefore weakening the muscle contractions. Now, dependent on the fitness level of the athlete, the OBLA, or the onset of blood lactate accumulation, will be sooner or later. So the lactate level in the blood is going to build up sooner if the athlete is less fit than if they are fitter. It will build up a lot later and will be a delayed OBLA. Fatigue during this type of exercise can be avoided by glucose injection, like little glucose, liquid glucose pouches things, or carbohydrate loading days before the event to boost the glycogen stores, because that is the primary energy source being used. So the effect that fatigue has on this specific performance is that it may reduce the performance towards the end of the race if the athlete hasn't paced themselves. Also, less power can be generated, which is specifically important in the legs in this race. So this type of exercise takes a while to recover from due to the build-up of lactic acid and hydrogen ions being left in the blood, therefore increasing the acidity because of anaerobic respiration. So this is a graph just showing any type of exercise. It's just to point out which parts go where, like the key, so you can see the oxygen deficit and the different types of recovery. So if we were to use a graph that was specific to this particular activity, we would see a fairly large oxygen deficit and therefore a large epoch for the repayment of oxygen, because it is an anaerobic activity. Now, because of the use of the lactic acid system, lactic acid has to be converted. It can't just stay how it is. So 65% of lactic acid is converted to pyruvate, which can then enter the Krebs cycle and be used to make energy. 5% of lactic acid is converted into glucose, and 20% is converted into glycogen, which is stored in the muscles and liver. And also, they are both, glucose and glycogen are both used for the Cori cycle in the liver. And then 10% is converted to proteins. To recover from this type of activity, a lactic fast recovery is used, as well as lactacid slow recovery, which is getting rid of the lactic acid by oxidizing it, also replenishing glycogen stores, which can take up to 2 hours for this type of moderate exercise. Now, DOMS, or delayed onset muscle soreness, can occur after exercise like this, moderate or high intensity exercise. It's caused by myofibril tears from accustomed exercise, so if someone's not particularly used to using their muscles in this type of way, or certain contractions. It leads to pain, swelling, 24 hours to 48 hours post-exercise, and the strength of the muscle is impaired. Passive stretching will help recover from DOMS. Foam rolling will also help, using a foam roller to eliminate knots within the muscle. Now, submaximal exercise, such as a marathon, is very, very high in duration and low in intensity. So the primary energy system used is the aerobic system, using aerobic respiration. Now, glycogen is used as a fuel for this type of exercise, but also fat stores can be used, specifically if glycogen stores deplete quickly. Waste product of submaximal exercise is carbon dioxide and also water, but mainly carbon dioxide is the primary waste product. So the effect that fatigue has on the performance of a submaximal athlete is the rate of work will slow, and also the amount of motivation to continue might decrease. In order to prevent fatigue during a marathon or before a marathon, carbohydrate loading again leading up to an event helps avoid fatigue because it boosts glycogen stores, and also athletes can train themselves to use their fat stores a lot sooner, therefore saving glycogen. Recovery from this type of exercise is fairly quick, as we can see in the graph, recovery is a lot quicker than the maximal exercise graph. Also, there is a much smaller oxygen deficit, purely because steady state exercise or submaximal exercise uses oxygen when using the aerobic system. So there's a smaller epoch because there's less oxygen to pay back, because oxygen was being used throughout the exercise session. So also less lactic acid due to primarily the aerobic system being used. The only real waste product was carbon dioxide. So carbon dioxide is got rid of by a lactic acid slow recovery, which is helped by an increased cardiac output because more blood is then being pumped out, transported to the muscles to create carbaminohemoglobin, which obviously then can remove the carbon dioxide. Also ventilation, because more respiration means more carbon dioxide is being exhaled. Restoring glycogen stores can take days after a marathon. And also a lactic fast recovery to saturate hemoglobin and myoglobin with oxygen once again. So the last type of exercise is intermittent activity, such as a football game. So overall it's very high duration, but there are periods of rest within the game, and also intensity varies with different parts of the game, as well as the energy systems, which vary. So you could use the lactic acid system if you're constantly chasing the ball for a minute or two, or a header might use just a molecule of ATP, but overall you're running about for 90 minutes, so that is the aerobic system for you. So the main fuel used is glycogen. Also it's all the fuel really, so phosphocreatine, ATP, glycogen, but also fats can be used. So the main waste products are lactic acid from the lactic acid system and carbon dioxide from aerobic respiration. Fatigue can be avoided by ensuring that the athlete is hydrated throughout the game, and also they boost their glycogen stores beforehand. Intermittent activity, such as the game of football, is constantly changing. Plenty of impulses need to be sent around the body, telling the muscles what to do, as well as the body feeding back information to the brain about what's going on within the game. So because of many impulses being sent around to the muscles telling them to contract, the level of acetylcholine that's being transmitted across the synapses will decrease, therefore meaning further impulses will be slowed, having an impact on the performance, for example, decreasing motor skills of the athlete. Other effects on performance include decreasing reaction time, rate of play could slow, quality of the technique will also decrease, like the quality of passes, for example. So recovery can occur during the intermittent activity, allowing time for resynthesis of ATP and potentially boosting phosphocreatine stores once again. So this can happen during the game. As we can see in the graph, it's the different systems and how they play a part during intermittent activity. So many footballers use cryotherapy, which is, ice baths after a game as a recovery strategy. However, some use contrast water therapy, which is going from cold to hot water several times. This obviously tightens and relaxes the muscles, reducing loss in muscle strength and muscle soreness. Active cooldowns also allow heart rate to decrease and helps the removal of carbon dioxide and helps to prevent DOMS, delayed onset muscle soreness. So as we can see in the graph, ATP depletes almost instantly, and it's just the different systems and how they play a part. So obviously the overall performance can decrease towards the end, but the aerobic system is still continuing to play a part.